Okay, welcome to session 4 in digital circuit design using ADS. And my name is Anurag Nigam. And where we left was we did the universal gates, and we still need one more gate because it is used for parity checking, and it is also used for as a controlled inverter, or it is also used for, if it is a controlled inverter, it can be used as a ones complement circuit. Right, so that's a XOR gate. So I'm going to use transmission gates to design XOR gate, and I apologize that in my previous section I said that static gates, you need 8 transistors to implement a static XOR gate or XNOR gate, while in case of transmission gates also you need 8 transistors if you can consider all the inverters, right? But the advantage is, if you remember in session 1 I showed you a static XOR or XNOR gate. You see that there are 4 transistors which are stacked on top of each other. Okay, for any logic there would be 4 transistors, and that means that if you are designing for a given supply voltage, okay, then the overdrive voltage on each transistors have to be small, right? Otherwise, you will not get the swing. So that's the problem with the static XOR gate. So the number of transistors in a static XOR gate is same as the number of transistors in a transmission gate based XOR gate. So now let's make a new folder and call this as transmission gates. Okay, so the basic unit of a transmission gate is called a transmission cell, and I'm going to make a TX cell. Okay, just one second, let me again make a distinction, okay, as medium speed and high speed. Okay, so under medium speed I'm going to make a schematic called TX cell or a transmission cell, and we will see how it works. So what I'm going to do is I'm going to take a NOT gate. So let's look at a NOT gate. Okay, so what do you see? In a NOT gate, the VDD is 1 and ground is 0. So a PMOS device transmits a 1 and an NMOS device transmits a 0. Now we also see that in static gates the output is either connected to VDD or to ground, but there is no connection between input and output, right? That's the characteristics of a static gate, right? Now in a transmission gate there is a connection between A and Q through PMOS device as well as NMOS device to transmit a 1 or a 0. So basically a PMOS device will transmit a 1 and an NMOS device will transmit a 0. But this gives you another state rather than just 0 and 1. This gives you a high impedance state also. So when you switch off both PMOS and NMOS device, then the output would be floating. It will not be connected to anywhere. So that will be called Z or Z, right? So that can be used as a tri-state buffer. So let's make a transmission cell. So I'm just going to copy this. I'm going to paste this here, and I'm going to just twist them around. Okay, so how do you twist them around? Okay, so first I'll disconnect them. So I will rotate this device as this, and the source is always on the left side. So for this one also I'm going to rotate and then mirror it out so that the source is on the left side. Again, I don't want any tuning on this. Okay, so maybe from the main one also I should remove the tuning, because every time it gets copied. Okay, then save it. Fine. Okay, so now I have got 2 devices. Source is always on the left. Let me just mirror it the other way also. Okay, so source is always facing the input side like this. Now source is always at a known potential, and what is the known potential? The input. And then drain can be at a potential which is not known. So basically we are going to transmit between A as a input, and Q as a output, Understood? So now F5. Okay, so this is the situation right now. Okay, so this PMOS device is going to transmit a 1 when this input is low, the gate input is low. So I will call the gate input as CB. This is a control input, it's a control bar. So 1 will be transmitted if control bar is low. And the other side is going to be C, or a control signal. So NMOS will be on when the control signal is high. Right, so C is high, then 0 will go through. Right, so this completes it. Now the question comes is, where would I connect the, I cannot short it. If I short it, then there will be an issue, right? So because these sources are connected together, so I cannot short the source of one to the other, right? So what I'll do is I will have a VDD. So that VDD is for the PMOS device, the highest potential. And then I will have ground. That will be the for the body connection of the NMOS device. Okay, so this completes my transmission cell, and the symbol for transmission cell is also a quite standard one. You will see it everywhere in all the books. So you understood how this works. When A is 1, then PMOS transmits it. When A is 0, then NMOS transmits it. So for PMOS to transmit, CB has to be 0. For NMOS to transmit, C has to be 1. Okay, now if C is 0 and CB equal to 1, then both the paths are blocked. So when both the paths are blocked between input and output, then this Q is floating, and this causes the Q to be high impedance state. So now this cell can be used as a tri-state buffer. So transmission cell can be used as a tri-state buffer, and transmission cell is the key to all the gates which we design. So let's make a symbol for this one. So this would be under transmission gates. Okay, so let's make a symbol for this one. Okay, and I want the symbol to be very small because it's easier to make circuits out of these standard cells. So what I'll do is, maybe this is a good size. Okay, usually it's going to look like this, and you are going to have A on one side, Q on the other side, C on the top. This is a control voltage, I'm sorry. So C would be over here, and I don't want to confuse you, so I'll put the C over here. And CB I'm going to keep at the bottom here, and I need a bubble. Okay, so because I want to represent a bar, right? So this is going to be VDD. So I'm going to keep VDD over here like this, and then I have a ground. So I'm going to keep the ground over here like this. Now I'll make some adjustments by switching off the grid, right? So first thing I'm going to do is drag this down, drag the ground down. Second thing is I'm going to adjust this pin and keep the VDD up. So this is done. C I'm going to keep here, and CB I'm going to keep here, and I want to introduce a bubble here. So I will make a bubble. This is a good size of a bubble, and I'll keep the bubble over here. So this is the symbol for a transmission gate. So now what I'm going to do is, now this means that I can create a high impedance state between A and Q. If I make sure that if I have two paths to output, for example, right, which I'll see in the next circuit, which is a multiplexer. If there are two paths, if I assure that one path is off, then the output can be directly combined. In gates, you cannot combine directly the output, because you will be shorting out the supply to ground under certain logic situations, right, logic inputs. So in the case of transmission gates, you will not have a problem, because one of the branch can be high impedance. So that's why you can connect two branches, the output of two branches together. In gates, you can never do that, because they are based on pull up and pull down, and you can create a short between VDD and ground for certain inputs. So that's why gates are never connected as it is to the output. Okay, so this is the difference we should know, that this has an additional one state which is a high impedance state. Okay, so let's do that. Meanwhile, as customary, I would go here and say copy cell, and I will call this as copy cell HS, or a high speed, right, high speed, and I will copy this to the high speed folder as a high speed folder. Okay, so I have copied that to high speed folder. Now here I'm going to rename this so as to make a distinction. I want this to be called MS. So don't worry about what happened to the symbol. Okay, here the symbol is the same. I'm going to add a text here which says that it's going to be high speed symbol, HS. Okay, so we are done with this part. Okay, so now let me just modify this. So I'm going to open a high speed inverter, which is a NOT gate, and copy two transistors from there. Control C and Control V. Done. And here I can throw this out, right? So this is going to be the NMOS device. So I'm going to rotate this and put this over here. Oh, now you should be careful what has happened. So I'm going to undo this first. Okay, what has happened is I forgot to turn on the snap grid option. Okay, now I will do that. Control V, and now I'll throw this, rotate this one out. Source is on the left side. Move the text, and this one I'll throw out and replace it with the PMOS. Okay, and the source is on the left. Okay, so now the real question becomes is the speed of this transmission gate will depend on the channel resistance and what capacitance it is going to drive. Okay, so the capacitance would be usually the gate capacitance of the gate it is going to drive. So if you have a very large channel resistance, then the circuit is going to become slower. For that reason, I'm going to increase this to, let's say, 2, and increase this to 4. Okay, so this is to reduce the RC time constant for the delay, right? So this is done. So now we have got two of these transmission cells. One is for the high speed, the other one is for the medium speed. Now let's make a new circuit called MUX. Okay, new schematic. I will call it as MUX 21 MS, medium speed. Okay, so now I can use two transmission cells for the two inputs, right? F5 and F5. Okay, so I'm going to make sure grid is on, right? Okay, so now I am going to connect VDD first. So this will be VDD, and I am going to name this node as VDD. So you need not do a physical connection, you can just name them and it is going to get connected. ADS is going to netlist it that way. And then what I can do is I have another pin which I am going to say is ground, right? So I'll keep it over here and call this as ground, and then name. So I can name this as ground, so the ground is connected over here. Name this as ground, so the ground is connected here, and this pin is ground. So done. Now as far as the connection for control bits, they are connected in tandem. Why they are connected in tandem? Because at any point of time I want only one of them to be on, because the output is going to be combined together without anything in between. This you cannot do in gates, because gate doesn't have a high impedance state. This you can only do in transmission cells, because you are assuring that one of the path is going to be open. So that way there is no problem of loading on here, right? There is no problem of shorting the VDD to ground as it will be there in the static gates. Okay, now I'm going to have I0. So before that, let me just put here a control signal, right? So every mux has a select line, right? So I will call that select line as S0. S0. So that S0 is the select line. So if S0 is low, right? So if I was to connect this over here, so if I was to connect this over here, then I have to create a S0 bar, right? Which will be connected over here, right? So I need to introduce S0B. So I have to introduce S0B, and that would be connected to, sorry, I don't need to do that. What I need to do is I can put an inverter here, right? So I will take an inverter from the medium speed cell, which is a NOT gate MS, and I will put it over here, right? And I will move the text out of the way, and I will just say this is connected here, and this is connected here, and this is VDD and this is ground. So I will name these pins as VDD and ground, right? So now this is VDD and ground. Maybe I can move the text over here. Okay, so now we have a control logic which is already figured out. Now the question is, if S is 0, that means that this path is through. So if this path is through, then this will be called I0. Sorry. Okay. And then the other one will be called I1. This path is through. Again, I'll move the text out of the way. Okay. So if S is 1, then this path is going to be through between I1 and Q. And if S is 0, then this path will be through between I0 and Q. And then all you need is a Q. Okay, so this is a simple 2:1 mux. Now let's count the transistors I'm going to use. Okay, so let's count the transistors, whether I was correct or incorrect. Okay, let's align that for this to look neat. Okay, so this is a mux, 2:1 mux. I0, I1, VDD grounds are all connected. This is a control line or a select line. Okay, so let me see. There are 2 transistors over here, 2 transistors over here, and 2 transistors over here. So I was right. So I need 6 transistors only for a mux. But for a XOR gate, I would need a NOT gate here. So that would require another 2. So 8 would be required for a XOR gate. Only 6 will be required for a mux. And you can create any gate using mux, right? So that's a a basic gate here in front of you, right? So let's make a symbol for this. Okay, to make a symbol for this, mux, and say new symbol. Okay, it should look like a mux, right? So I0, I1 and S0 and VDD. So I'm going to rotate these, keep them aside. Ground, I'm going to rotate this way and keep it aside. And this is my output between S0 and S1. And this I can bring down like this, and this is my ground. Sorry. And this is my select line. And this is going to be my VDD line. Correct? And this I can move here. Okay, I need to do one thing. I'm not happy with the symbol. So I'm going to just make my own symbol. So use a polyline. What I want to do is the following. So it should look like a mux now. So it looks like a mux now. Okay. And then I need one line, medium, which I'm going to connect this way. Okay, so now it looks like a mux. So now this looks like a mux, and I'm going to just put it in the center. Okay. So when S0 is 0, then I0 goes through. When S0 is 1, then I1 goes through. So that's a mux. Okay, so I have made a mux. Let's make a copy of this as a high-speed mux. So I would say copy cell, and I'm just gonna copy these, and I'll change the prefix to HS, and I will copy to high-speed folder. Okay, and say OK. So it's over here. I'm going to make minor modifications. So this will be HS. So it is as good as just changing the name. So this is a high-speed cell, and this one is going to be a high-speed gate, HS. So I have converted the mux to a high-speed mux. Done. Okay, and the symbol, I'm going to just introduce a text. Insert text. Okay, and I will introduce HS over here to make a distinction. So this is a high-speed mux. Done. Okay, so now I'm not going to text the mux. I'm going to text an XOR gate. So I'm going to make a new schematic, and I'll call this as a XOR. Or rather, I can use a NOR gate, right? Okay, so I'll tell you why I'm going to use that. I'm going to copy cell NOR gate. So if I go to NOR gate, I'm going to say copy cell, and I will call this as a XOR gate. XOR gate MS, and it will go to transmission gates medium speed. So I have a XOR gate over here. So all these things are fine. I just don't need any of this stuff, right? Okay, what I do is I just introduce a mux here to the output. So there is a mux to the output. Okay, and one of the inputs is going to be the select line, other input is going to be VDD and ground. So let's say A is the select line. Okay, that means that, okay, let's move the text out of the way. Okay, that means that if A is high, then I1 goes through. If A is low, then I0 goes through. So it's very simple. Then put the other one here. So if A is high, B bar goes through. So you introduce a NOT gate here. Okay, so I'm going to go down and copy the NOT gate. Control C, Control V. So move the text out of the way. Okay, fine. So when A is high, B bar goes through. And when A is low, B goes through. So when A is low, B goes through. And when A is high, B bar goes through. Correct? And then these are VDD grounds. So I can put here VDD. And I can put here ground. Okay. So I'm using a mux to design an XOR gate. Okay. So this is the design, right? So when A is high, then B bar goes through. So that is what A dot B bar. And when A is low, B goes through. That is A bar dot B. And the result is a XOR gate. Okay. So I am going to modify its symbol. Okay. So what I'll do is very simple. I'll just copy this over here. And I am going to put here, I'm going to turn off the grid. I'm just going to put here a round thing like this, and I am going to put here a line like this, and as the grid is off, I'm going to take advantage. I move that closer, and I'm going to turn back the grid on. So this is the symbol for my XOR gate. I will center it here like this, and I'm done. So what you have here is a XOR gate which I have generated. Now let's test the XOR gate. So to test it, I am going to use the same test bench. So let's pick up a test bench of NOR and say copy cell. So test NOR is I'm copying. Let's make it XOR and put it under transmission gates medium speed folder. Say OK. Okay, so we have it over here. All I do is I change this to XOR gate MS. Slightly moved, but I'll move it back. Okay, so now I have an XOR gate which I can test. So to test this XOR gate is just run it. But okay, so I'm gonna just run this. Okay, meanwhile I'm going to copy the display from the NOR gate. So I'm going to copy this entire thing, Control C, and whenever the display opens I will do a Control V. Okay, Control V. Okay, I'm not getting the output. The reason being that Q is gone. So let's name this again. Okay, let's do this again. Okay, so now you see that because the paths are not matched, you are going to get these, right? And these spikes don't look good, right? This is because the paths are not matched. So how do you minimize them, right? There's another way I can do this, is I can go in, implement this as a XOR gate, and then invert the output. So those spikes would be gone. So what I'm going to do is, now the same thing is going to become a XOR gate. Correct? So now this is a XOR gate, and then I'll put one inverter to get rid of those glitches. So I can take this inverter and put it over here. One inverter I can put over there. Copy of this. I'll put it over here. F5 text over here. So now the same thing is going to be an inversion following the, and this inverter will take care of those glitches, though this will increase the delay, right? Okay, so now let's see what happens now. Okay, it's done. Okay, so the glitches are gone, but then there is a problem. You see, you introduce an additional delay over here, right? So now if you were to use this XOR gate, for example, in adders, now there is an additional delay here, right? So if you cascade lots of full adders, then the frequency of operation is limited now. So if you were to implement this XOR gate if you want to use XOR gate to implement a full adder, you have to use the previous version, because this version will give you a delay, and that will limit your frequency of operation. So this I'm just explaining. You can always do on the fly. So if this one doesn't work out good, you can just go ahead and revert the changes here which we have done without affecting the functionality. But anyways, let's test this. So when both inputs are high, output is 0. So it's an even parity. When it's an odd parity, output is 1. Again, when it's an odd parity, output is 1. When there is an even parity, output is 0. So this is how a XOR gate would work. Now I can just do a high-speed version of this one. So have I done a high-speed version of this one yet? Not yet. So I'm just going to say copy cell, and I will say XOR high speed. So I'm going to name this as high speed and change the folder to high speed folder and say OK. So where did it go? Okay, it is over here. Now here all I have to do is change this to HS, change this one to HS, and change this one to HS, and we are done with the high-speed XOR gate. So I'm not going to test it. So as we go further, I'm going to stop testing these again for a high speed and low speed. Okay, when we go to a critical circuit, there I would check it. So this is my XOR gate, which can work in tens of gigahertz. Fine. So we design XOR gate and we tested it. Do I need a XNOR gate? I don't see a reason for a XNOR gate, right? So if I don't see a reason for XNOR gate, I'm not going to do it, though you know how to do a XNOR gate, because XOR gate so you know what is XNOR gate. Okay, so this is how we design a MUX and XNOR gate, XOR gate, sorry. And I'm going to stop this session here, and next we are going to do some sequential circuits, right? So thanks a lot.